So here's an outline that I don't have up there. So this is kind of an interesting one. So we're going to learn how we start oxidizing fat, burning fat. This is our fat burning lecture. And then we're going to figure out how we kind of review how we get energy from that. And then we're going to talk about what if we don't have adequate calories or carbohydrate. So we'll talk about ketone production and ketogenesis and potentially some of the effects of that. And then the last part, we'll make fat, okay? Synthesis of fatty acids and how that's regulated. So let's talk about the first part of this. Remember, so now this is kind of how we use fat that we've stored for energy. So one of the things to keep in mind is enzymes and hormones that are involved in that. So if we look at this slide, this is shows a fat cell, adipocyte, aka adipocyte. Depends if you're tomato. And this is one cell, and its primary function is store fat. And it stores fat as triglyceride. And so you look at these cells, and if all things are good for them, they'll have like 80% of their volume triglyceride. And the triglyceride droplet expands and kind of pushes everything out of the way. So if you look at these, they'll have like their nucleus and their mitochondria, cellular organelles kind of shoved off to the side. And their primary focus, store triglyceride. And this doesn't show it, but there's a fascinating area of research that looks at the proteins that surround that triglyceride droplet. And there's paralipins and all different kind of proteins that are involved in regulating how much fat we can actually get from that droplet. So it's really interesting, and that's something that is very important research, because one of the things to think about is, do we need fat cells? Absolutely. They're crucial for storing a very dense energy source. But the question is, how to keep them working properly. We want them to be able to store fat when we need to or want to, but also let go of that fat when they need to give us the metabolic flexibility to store energy and then burn it when we need to. The problem is if we have too many fat cells, or if they get too big, it can cause health problems. And remember, we're talking about mostly subcutaneous fat. We're not talking about visceral adipose tissue. Have you ever heard that term? Visceral adipose tissue, some people say, oh, it's abdominal fat, things like that. That's basically a type of fat that's intra-abdominal around our organs. That tends to have significant health effects. And it's very interesting. That's one of the latest areas of research that are looking at. We have some preliminary data where we've actually seen, again, in general, women have about 10% more body fat than men. And yet, significantly less visceral adipose tissue. Another thing that we do wrong. But that's another potential health implication. I thought that was very interesting. We've got that in some of the research people we've had in ours. I don't know if anyone else I think one or two other groups have looked at that and observed that. We haven't published it yet, but hopefully we will soon. There's a relationship between that and HDL cholesterol, which is very interesting. So the kind of fat we're looking at is the kind that's supposed to store triglycerides and then release them when we should. So that's a fat droplet. And it says this little black circle filled in, that's hormone-sensitive lipase. So that's the enzyme that breaks down the triglycerides, hormone-sensitive lipase. How do you think it's regulated? Hormones, right? And so we're going to look at how it's regulated. So look what it does. It sits in the cytosol until it's phosphorylated. And then when it's phosphorylated, it catalyzes the release of fatty acids from the stored triglyceride droplets in fat cells. So it works wherever adipocytes are found. It also, hormone sensitive lipase is also in some other tissues, including muscle. Did you know you have fat in your muscle? A little bit of triglyceride in muscle fibers. And again, doesn't make sense, but the better shape a person's in, the more fat they have in their muscle fibers. Right? It can be an additional energy source for that muscle cell. So it's a little counterintuitive there, but so that's not just in fat cells. Hormone sensitive lipase is also in muscle tissue. Okay, works a little bit there. Okay, so here's what it does. Once it's activated, moves to the surface of the triglyceride droplets and starts hydrolyzing off fatty acids. The fatty acids, this is free fatty acids. Now what happens to them? The free fatty acids start accumulating. They run down their concentration gradient out of the cell. Right? And then they'll leave the cell, go through the endothelial cells, and bind to albumin in the blood. Again, albumin is providing a place where those hydrophobic fatty acids can kind of hide as they move through the blood. Okay? Now what we're going to do is we're going to follow that. We'll talk a little bit about the regulation here in a second, though. Here's another way of looking at this. So here's how it's regulated. The fed state. Insulin decreases hormone-sensitive lipase activity. Have you ever heard anybody say, oh, don't eat carbohydrate, it minimizes fat oxidation? Kind of true, but the upside outweighs that. So we'll talk about that in a second. During fasting or exercise, the stored triglyceride is used as a major energy source, right? It's very important. Glucagon and epinephrine actually activate hormone-sensitive lipase. So in times of lower blood glucose or exercise, and in general, when we exercise, blood glucose drops. So insulin drops. That allows us to maximize fat oxidation. And so it allows fatty acids basically to leave storage and go into the blood. And here's a cellular way of looking at that regulation. So this shows cytosol of a fat cell, the surface of the fat cell. Fat cells have epinephrine receptors. They have glucagon receptors. They have insulin receptors. So they can respond to all three of those hormones, right, which are regulated at different times. So if we're sitting here and a person hasn't eaten for a while and blood glucose drops, glucagon goes up. And that's promoting fat oxidation. And so typically if you're in this scenario like now and you haven't eaten for, like, let's say a couple hours, probably 75% of your calories are coming from fat. And it's glucagon, in that case, that's helping that. As soon as you start doing something physically active, epinephrine also goes up. Like now, if you left here and you went to the rec center or whatever and started exercising, epinephrine goes up. Matter of fact, let me give you numbers because they're pretty significant. But now look what happens. If either glucagon and or epinephrine are in the blood and they bind to their receptors, they stimulate the phosphorylation of the hormone-sensitive lipase, and that activates it. Insulin does the opposite. And remember, they're gonna tend to be opposing levels. So if glucagon is up, insulin is down, and vice versa. So this is why somebody says, you know, as soon as you consume carbohydrate, you minimize fat oxidation. Kind of. I'll tell you why that's not completely true in a second. But how does this work? So let's look at this regulation real quick. And I can post a table on this if you want. So these are, I think it's worth going through this. These are concentrations of, these are blood concentrations. to say of free fatty acids. Glucagon. And epinephrine. And this is in millimolar. This is picogram per mil. Right, peptides here. Picogram per mil. This is at rest. 329 lecture. Free fatty acids. Are there any free fatty acids in your blood? 0.43 millimolar. 77 glucagon. 75 epinephrine. Now let's say you go over to the rec center and there's a grad student there and they say, doing my thesis, my advisor has a little bit of money for this project. I'll give you $50 if I can follow you in there. You sign this consent form, and you're like, yeah, I'll sign it. $50. And you go in there and you sit on the bike, right? And they're like, you fasted, right? And they're like, yep. And they go, okay. And then they stick they do a puncture into your arm and they take a blood sample. And they're like, okay, now we have your resting values. Okay, start exercising. And you're sitting on the bike going, oh, this is great. Just made $50. 40 minutes in. It's gone up. So what does this mean? Hormone sensitive lipase has been activated. What activated it? Glucagon stayed about the same. There's your major effector. 262. You're like, man, how long are we doing this? And they're like, it said it in the consent form. You signed it. Keep pedaling. I think this is about 450. The table online, I'll plug it in there. Now, what's going on here? Yeah, blood glucose is struggling now, right? You're tapping into that glucose and it's gone down. So glucagon is responding to that. But look at epinephrine, continues to elevate 90 minutes in. This is typical for all you guys, right? 120 on that exercise bike, right? Still gone up. Three hours later. No, you read before you sign stuff. Kind of interesting, right? 3 hours. Look what's happened. What fold increase do we have approximately? 5. So you can look at this like, fat in this person's blood's gone up 5-fold. Those are free fatty acids that are coming from adipose tissue. It's stimulated by glucagon and epinephrine, right? So that fat is a significant energy source. It's going up, but a lot of those fatty acids, if I'm on a stationary bike and I'm doing that, where's most of that fat going? Leg muscles. That's where it's being used, right? That's where the energy source is required. So I'm moving fat. Let's say for me, I'm moving fat from my abdominal area. That hormone-sensitive lipase is being activated. It's going into the blood, and now the fatty acids are going into the muscle fibers in my legs. And that's what's giving me the energy for that. Is this high-intensity exercise or low? For me, it's really low. If I can do this for 3 hours, that's kind of low-intensity exercise, which means you probably have adequate oxygen amounts to burn this fat. That's the other thing that's going on here, right? It's a really nice system, right? If you do low intensity stuff, you still get significant activation of fat going into the blood, and you have oxygen to burn it and use it for energy. Okay, so here's the tricky part. People will say, as soon as you consume carbohydrate after exercise, you stop fat oxidation. Not really, because look at what happens. Now you get off of this, you got off that bike. Now what's going to happen to this free fatty acid concentration in the blood? It's going to drop. Why? It's going to run into tissues. And at that point, now I'm resting. I have plenty of oxygen. I can still continue to burn that fat. Have you ever heard that? Even after you do one of these workouts, you're still oxidizing fat at an elevated level. That's true. Is your caloric expenditure still elevated? Absolutely. And it will stay elevated for quite a bit of time. If you did an exercise like this and it was kind of high intensity, sometimes that'll stimulate your metabolic rate for 24 hours. You'll have higher than normal metabolic rate. That's one of the things. That's one of the reasons. Like if your person's trying to do this, the more often that you can do it, especially at a higher intensity, the better, because you keep that metabolic rate faster. And that's one of the things that's happening here. Now, if a person consumes carbohydrate, yeah, it'll inhibit hormone-sensitive lipase, but I've already got all that fat in the blood. So that's fine. I can still oxidize the fatty acids even though I stop more fatty acids going into the blood. So that's one of the benefits, and that's why basically it's okay to say, yeah, after you exercise something like this, you should probably have carbohydrate or something to kind of help recover. Carbohydrate, probably a high-quality protein source to help recovery, because now you're storing that glycogen. Now, it doesn't mean that you weren't burning carbohydrate from this. It just means that fat was also a significant energy source. Because in general, when we exercise, it's a combination of carbohydrate and fat. And there's ways we can do this. Now, if they had done this, they can put you on what's called a metabolic cart. You'll see it next quarter in 329. They have, you guys are going to be under a canopy system when you do this, but there's face masks that you can put on. You've seen pictures of that, right? You get on those, and you can do a metabolic cart. That metabolic cart will tell you exactly what percentage of your fuel is coming from carbohydrate versus fat, and you'd see that it's a combination. All right? So one of the points of this, carbohydrate can help us oxidize fat. And that's what we're going to talk about coming up in a few minutes. Okay, so we talked about that. Now, let's follow this through and we say, well, how are those fatty acids being used for energy production? How do they provide energy for my physical activity? Well, they can be oxidized to produce FADH2, NADH, and acetyl-CoA. And we'll look specifically at it. Remember this? Per weight, fat has more calories, right? We'll talk about why in a second, but it actually yields more ATP than glucose does. And beta-oxidation is the major pathway of oxidizing fatty acids for energy. Remember that? I talk about beta-oxidation in biochemistry? Or somewhere, hopefully. Remember that occurs in the mitochondria. And why is it important that it takes place in the mitochondria? ETC and Krebs. So now let's follow those fatty acids from the fat cell through the blood into the muscle fibers. So we're going to go to ATP from this. Wherever. Another protein that looks like calbindin, right? Let's say this is a muscle fiber. When this fatty acid goes into the muscle fiber, it's activated by the addition of coenzyme A. Activation means adding the coenzyme A. It occurs in the cytosol and it requires 2 ATP. The enzyme is fatty acyl-CoA synthetase. We've talked about that enzyme before, remember, in intestinal cells. We say fatty acids go into the intestinal cells, CoA is added so that the fatty acids can be used or attached to other molecules. In this case, what's happening is that CoA is essential for that fatty acid to go into the mitochondrial matrix. So you want to remember this reaction. Fatty acid receives a coenzyme A. It requires 2 ATP to do that, because ATP converts to AMP. And now you have basically fatty acyl-CoA means a fatty acid with a CoA attached. That's all that means. So now CoA is attached. And here's why it's important. The fatty acid moves through the outer membrane of the mitochondria. That coenzyme A cannot go through the mitochondrial inner membrane. So an enzyme removes the CoA, transfers the fatty acid across, and then adds CoA back. Right, so this goes like this. CoA is taken off, fatty acid goes through. On the inside, it picks up CoA, and now it's fatty acyl-CoA on the inside. It's a different CoA molecule. CoA doesn't go across that mitochondrial inner membrane. So here's the trick. In order to get the fatty acid through, carnitine is used. And here's carnitine. So this is just showing the mitochondrial inner membrane. And carnitine is needed to transfer the fatty acids into the matrix. Carnitine is a very small molecule. It's made from 3 amino acids. Our body generally makes as much carnitine as we need, so you don't have to get it from Amazon or bodybuilding.com or anything. It's a fairly common supplement that kind of goes through waves and how common it is. And you'll see the promotion. You can imagine what the promotional campaign is. Hey, we have to have carnitine to burn fat. Don't burn more fat, have some carnitine. We make carnitine. So in general, probably not effective for, there's some applications, but for most people, you don't need to take it as a supplement. But that's what's going on. The carnitine replaces CoA, moves it through the inner membrane. Now we're on the matrix side. Carnitine comes off, CoA is added. That's all this is trying to show. There's actually 2 enzymes that are involved. Carnitine acyl transferase 1, CAT1, CAT2, don't worry about them. Now we're in the matrix. Now we have an activated fatty acid in the matrix of the mitochondria where Krebs cycle is and ETC. Where'd that fat come from? Wherever I had it stored. That's what's so interesting about this. We move fatty acids through the blood, and they end up going into the mitochondrial matrix of the cells that need the energy. Okay, so let's talk about beta-oxidation. Hopefully some good memories here. So here's some steps. Again, it just says stuff. Next slide has a nice picture. So let's read through this real quick. So kind of in step 1 is activating the fatty acid in the cytosol, and that allows it to be transferred into the matrix. And now we have oxidation. This is the first step of oxidation, and this uses FADH2 to carry the electrons. and then the molecule's hydrated, and then we have a second oxidation step, and then the last step, 2 carbons are cleaved. So the fatty acid gets 2 carbons shorter. So an easy way to remember this is activation, oxidation, hydration, oxidation, cleavage. That's what we're going to look at in a second. Okay? This is the way I like to look at it. I haven't changed this. If you look in the textbook, sometimes they'll have a circular pathway, right? For me, this is an easier way to visualize it, but whatever works for you. So up at the top is a fatty acid, and that's palmitoyl-CoA. And you'll see in a few minutes why it's very likely that that's palmitate. And it's because when we make fat in our body, we tend to make palmitic acid, palmitate. So we have a lot of palmitate in our body. There's also a lot of palmitate in a diet. Animals do the same thing. When they store fat, they typically store it as palmitate, palmitic acid. And so it's very, very likely that the fatty acid oxidation involves palmitate. So palmitoyl-CoA just means palmitate with CoA. That's all that means. So if you look up at the top, you can see that's abbreviated kind of shorthand way of drawing it. But palmitate has 16 carbons. 1 and 12 here, that's 13, 14, 15, 16. And then CoA, we're not counting those carbons. Okay? So where are we? Big picture in the matrix. This beta-oxidation in the mitochondrial matrix. First step, oxidation. And what does that mean? Pulling electrons. So palmitoyl-CoA is oxidized. So what happens? 2 electrons come off. The electrons are part of hydrogens in this case. So see the CH2CH2? That changes to CH-CH. Where the hydrogens go? Added FAD. Okay? You don't have to remember this enzyme, or this enzyme, or this enzyme, or this enzyme. No enzymes required on this page. Okay? But look what we did. Fatty acids still the same length, but we've pulled electrons off, and those can be used for ETC. So we've already got 2 ATP from this. Okay? Next step, hydration. And that's basically to add hydrogens. So now look what happens. Now we got a hydrogen, an OH added here, and a hydrogen added here. So that waters used to rearrange the molecule and provide more electrons. Now the next step, this dehydrogenase uses NAD as a coenzyme. So again, pulls off 2 electrons, adds them to NAD, so we end up with NADH plus a proton. There's NADH for ETC, that's 3 more ATP. So we've already got 5 ATP. Haven't shortened the molecule at all, just oxidized it twice. Last step is cleavage. So now look what happens. On this end of the molecule, see this CH2 and the C right here? If you look at that, you might not have memorized it yet, but this is essentially acetyl-CoA. Here's acetate. So there's an enzyme that basically adds a hydrogen here and then cleaves right here. So what do you end up with? Acetyl-CoA comes off. And how many carbons does acetyl-CoA have? 2. Right, so basically in this step, we remove this. And now what is that? That's acetyl-CoA for Krebs. And one of the reasons I said, I want you to remember that one rotation of the Krebs cycle can yield 12 ATP. So now look what happens. Now you can put that into Krebs cycle, get 12 more ATP. We've got 12, 17 just from this. We've only lost 2 carbons. We started with 16, now we're at 14. So you know what? Do it again. Wash, rinse, repeat. All right? Now we're going to do it again. So now what happens? Goes back up. So see that arrowhead up there? It goes up to step 1. So obviously this is a complex of enzymes that are doing this. And they'll kind of reshuffle. And now what do? You do it again. Oxidation, hydration, oxidation, cleavage. Now you have 12. Do it again. Then you have 10. You repeat these until you're at a step where you have 4 carbons, a 4-carbon fatty acid. And then what happens? It just splits. So here's what happens. Each cycle removes 2 carbons that are used to make acetyl-CoA. Then you repeat it until you have 4 carbons left, and then you split it. So the last time you go through, you don't need another cycle. So in your notes, I would put this. And you can also, but this is a good one. You do not need to memorize each step, but you do need to know the principle. So I'm not going to make you draw this. Okay? Here's how you figure out cycles. The number of cycles equals the number of carbons in a fatty acid. The number of cycles equals the number of carbons in a fatty acid divided by 2 minus 1. That makes sense? So if this is 16, divided by 2 is 8, minus 1 is 7. So what you do need to know is if I tell me the maximum number of ATP that can be made from beta-oxidation of a fatty acid that has 12 carbons or 20 carbons, right? I'll always give you an even number of carbons. Because you can imagine, oh, what if it's got 13? Now when I go down the end, I'm at 5. I got propionyl-CoA and acetyl-CoA. Now what do we do? I won't do that. What if fatty acid's unsaturated? Would that generate less or more ATP, theoretically? Less. There's less electrons. There's less hydrogens. It'll always be saturated. Okay? Let's walk through this in this way so that there's a table. So for example, palmitate. 7 cycles. For every cycle, just from oxidation, you get 5 ATP. All right? Let's say this is 1 cycle, 5 ATP just from that. And then the last step is, well, now I got acetyl-CoA. Every time I get acetyl-CoA, I can get 12 ATP. Here's another important point. In your notes, make sure you have this. Every carbon of a fatty acid with an even number of carbons becomes part of acetyl-CoA. Every carbon of a fatty acid with an even number of carbons becomes part of acetyl-CoA. So with palmitate, 16 carbons, you just divide by 2. Because every carbon is going to be part of acetyl-CoA. Acetyl-CoA has 2 carbons. So you just go 16 divided by 2 gives you 8. So you just calculate. If it's a C12, you get 6 acetyl-CoA. And because every acetyl-CoA, we can generate 12 ATP, you just take the number of acetyl-CoA times 12, and you get 96. If it's not clicking now, look at it again tonight after you have some carbohydrate but before you insulin crash. But look at it later tonight and just go, oh, okay, now it makes sense.
So the 5 is fixed for any molecule?
Yep. Yeah. So on the first one, you're just doing cycles times 5. The next one, you're just going, how many acetyl-CoA? Times 12. Now, that's gross. Net, you got to subtract your activation. Right? When the fatty acid first went in, you had to invest 2 ATP. It's not much of an investment, though, is it?
So you only need the 2 ATP in the beginning and it just continues to cycle.
Yep. Be able to calculate the number of ATP that are made from saturated fatty acids of different lengths that I just went through. Right? And that, again, that'll be in the study guide. So here's something to think about. Let's say I have a C18 fatty acid. You could do this, right? You could calculate this if I said, okay, do this for a C18 saturated fatty acid. Maximum number. Can't do the fatty acid beta-oxidation under anaerobic conditions, right? Can't do that. All of those ATP require oxygen. So now what would you expect here? And the clue is which one has more calories. So you can think, well, there must be more energy in here. So calculate this. I would recommend calculate this at home. And then this is 18 carbons, so what's fair here? 1 glucose? That'll give you 18 carbons. Which one do you think will give you more ATP? Top of your head, just like, I think this one, it must. Look at the numbers. And there's 2 main reasons why. One reason is this. Fatty acids have greater potential energy because they have more electrons available for ETC. They have more electrons available for ETC. Look at the structure. Think about the molecular structure. If you look at a fatty acid, right, and we looked at this before, this fatty acid's saturated with hydrogens. That's where the electrons are. Now, if you compare that to glucose, glucose has oxygen in there, right? So the glucose molecule doesn't have as many hydrogen electrons. So their molecular structure sets them up so that fatty acids have more ATP. They have more electrons. Again, as long as there's oxygen, we got great energy source. What's the other reason? How many acetyl-CoA are you going to get here? And I'm not going to tell you the answer for glucose. How many acetyl-CoA? And that's where you get a lot of the ATP, right? Acetyl-CoA into Krebs. What about here? Do all of these carbons end up in acetyl-CoA? Why not? Where? You go from 6 carbons here, right? You get 2 pyruvates. So you got 6 carbons, but you only get 2 acetyl-CoA out of it. So you lose carbons in the bridge step. So you produce less acetyl-CoA per carbon from glucose. So those are the 2 main reasons why fat is has more potential energy. Caveat is oxygen. So in other words, if we don't have adequate amounts of oxygen, then we lose the ability to burn our most effective energy source. So here's, have you ever heard this? Fat burns in a carbohydrate fire? Anything corny like that? Any corny sayings about that? Another, what else do they say? Fat burns in a fire ignited by carbohydrate, right? Funky stuff like that. They've been saying that for a long time. So in other words, if you look at this, what does it mean? Carbohydrate supports burning fat. Right? That's considered to be an optimal situation where you have both adequate carbohydrate and fat. So here's one of the things to think about. The premise for that is here. Now, we're only looking at one fatty acid. For example, every triglyceride has 3 of these. A lot of times when we look at this, we go, oh yeah, then acetyl-CoA combines with oxaloacetate, goes into Krebs. And we think about this just as kind of going around in a circle. Oh, grab another acetyl-CoA, run it through, right? I have a lot of fat. If I start burning that fat, I can generate a lot of acetyl-CoA. So now rather than just thinking about, 8 here or something, think about 1,000 of them. Every one of those acetyl-CoA molecules has to have oxaloacetate to combine with. So what happens if we're maximizing fat hydrolysis, but we run out of oxaloacetate? If you think about it, what scenario could that be? High fat, low carbohydrate diet. If we minimize carbohydrates, we can actually cause oxaloacetate to be rate limiting. And here's why. So if somebody says, I don't need carbohydrate, do whatever you want. But if you look at this reaction, that kind of goes against that. Let's say we're burning fat, and this is the liver. This is from a sports nutrition text. You don't have this in yours. So we're in the liver. And the liver is one of the tissues that burns a lot of fat. And even, for example, when we're burning significant amounts of fat in other tissues, the liver can run on fat. And one of the reasons is because the liver always has oxygen. If your liver doesn't have oxygen, that's lethal. Right? So the liver is always doing this. Other tissues kind of change how much fat they're burning based on oxygen levels. But anyway, the reason we're looking at the liver is this is a good diagram to show this. Here's an alternative reaction. I don't know if you've ever seen this in other classes, but pyruvate doesn't always become acetyl-CoA. Pyruvate can also become oxaloacetate. Main source of pyruvate, carbohydrate. So this is kind of what's happening. Let's say, for example, we're burning a lot of fat. We're oxidizing fat. And we're getting a lot of acetyl-CoA. And every time we have acetyl-CoA, we need oxaloacetate to combine with it. Here's another acetyl-CoA. We'd also need another oxaloacetate to combine with that. So again, let's say we're generating a lot of these. What happens if oxaloacetate becomes limiting? Well, what a cell can do, like liver cells, is the liver sometimes can actually supplement this with, rather than doing this with carbohydrate, it'll do this. Because if carbohydrate is limiting and we don't have enough oxaloacetate, these two molecules can combine. If acetyl-CoA can't combine with oxaloacetate, acetyl-CoA can combine with acetyl-CoA. And the context is, let's say that's in low carbohydrate status. So guess what these combining result in making? What do we say? Oh, low carbohydrate diet, it's ketogenic. They make ketones. So that's what's happening here. Let's say, for example, carbohydrate is low. Pyruvate is compromised. The amount of carbohydrate is compromising pyruvate production. So you don't make as much oxaloacetate. So what happens? Acetyl-CoA molecules combine, and they become what's called acetoacetyl-CoA. And that can combine to make, that can be modified to make ketone bodies. And I'll go through all this in another minute, but that's what's happening here. Ketone bodies are made in the liver, but secreted into the blood. So when people say, oh, I'm on a ketogenic diet, if they are, and ketones are being made, they're being made by the liver. And why is the liver doing that? The liver's doing that so that extrahepatic tissues have an alternative energy source. So the brain and muscle can use the ketones made by the liver as an energy source. And another thing that's happening here is, if under those conditions where carbohydrate is limited, we're doing gluconeogenesis. And so this is what's happening. This is right here, right? When we go oxaloacetate to PEP to glucose, that's pyruvate kinase bypass. These amino acids are likely coming from skeletal muscle. So under those conditions with too low of carbohydrate, the liver starts switching over to ketone production. And it happens very quickly, like overnight. We start making more ketones than we did right after we ate. The longer we go, ketone production tends to go up. So after a few days, ketones in the blood can elevate. And your body is doing that to respond to basically the sense of starvation. And here's another reason. When a person first starts in starvation, they start losing muscle tissue extremely rapidly. And one of the reasons is because at that point, all of our tissues rely on glucose, like the brain and central nervous system. That's when this catabolism of muscle tissue is really high. And that's because the amino acids are being purged from muscle. The muscle's being broken down. Amino acids are put into the blood to provide substrate for gluconeogenesis. But what the liver does is, to minimize the duration of that, the liver decides we're going to make ketones. So the liver can make ketones to decrease our reliance on gluconeogenesis. Because now one of the main tissues, the brain that relies on glucose, can switch over to ketones. And that's what's happening. Now some of the catabolism continues. It can affect body composition. But it's basically a way of providing an alternative energy source to the brain and central nervous system that doesn't store carbohydrate. And it'll start running on ketones. Ketones can go across the blood-brain barrier. The caveat is it requires oxygen, which the brain always has. So if those go into muscle, you can't use the ketones during anaerobic activity. You're still relying on carbohydrate. But that's what's happening in this case, and it's because as soon as fat oxidation becomes the main energy source, carbohydrate can become limiting. And a lot of it has to do with that reaction of oxaloacetate being required to make citrate to enter into Krebs.
So what happens if you do anaerobic activity?
A lot of times the performance is compromised. So those diets have been around a long time, and I've trained a lot of people on ketogenic diets. It's harder for them in general. Some people can get around it, and they'll say, "Oh, I've been on it for a long time. I'm better at it now." But for most people, it can compromise performance in that case. I'm not saying it's not for everybody. I wouldn't rule it out for everybody, but I would say there's maybe potentially better ways to do it, because another thing it really does is it really changes food selection, and you move away from some really important sources of specific nutrients. So all of that person has to consider all of that. I just hope they're, you just kind of like in the class we're going to have here, right? We're going to talk about stuff like that. Like there's some other things to think about as well. So molecularly, that's kind of what's happening in ketogenesis, and we can talk about some of the effects next time. So I think next time let's talk about how we use them for energy and stuff like that. But if it's okay with you, I'll stop there. Okay. All right, guys. Thank you. See you Tuesday.